The formation of visual thinking of students in the technical universities in the context of higher mathematics education. Modern students differ from previous generation in their speed of thinking and preference for graphic information. But why do many of them struggle with understanding mathematics? The problem lies in the insufficient development of abstract and logical thinking. Modern students have unique thinking characteristics that require new teaching approaches. To some extent, this deficiency can be remedied by forming visual representation of some basic mathematical concept. The ability to freely manipulate visual objects is also an important component of the professional training of future technical specialists. In our study, we explored how the use of visual methods can improve the assimilation of complex material in higher mathematics. We believe that the information of visual thinking can significantly change the understanding of mathematical concepts. Our hypothesis is that activity developing these skills can effectively improve the learning process and contribute to the successful assimilation of complex higher mathematics material. Thus, we have taken the following steps to achieve our goal. First, investigate the current state of higher mathematics teaching and how visualization is used in the education process. 2. Develop a theoretical concept that explains how visualization can facilitate the understanding of mathematical concepts and increase student interest. 3. Create education materials using visualization method to explain higher mathematics content. 4. Test these education materials in learning environment to gather data on their effectiveness and student interaction. 5. Analyze the result to determine how successful and effective the methods and educational materials were in understanding mathematics concept. Scientific publications describe visualization in various ways. Some see it as the transformation of data into graphic forms, while others view it as the process of creating images for better understanding. People often perceived visualization and illustration as synonyms, but research shows that differences. Experts believe that visual images are not just illustration of thoughts but manifestation of the thinking itself. The differences between visualization and other illustration means lie in the fact that visual thinking is a mental activity in a special environment, allowing for transition between different types of information and understanding their contexts. Visualization plays an important role in systematizing and understanding concepts in higher mathematics course. It can help students transform abstract mathematical concepts in concrete visual images, making them easier to perceive and remember. We propose some ways to use visualization for systematizing higher mathematics concepts. First, using graph to display function, curves, differential equation graphs, etc. This allows for a visual understanding of relationships between different variables and the structure of objects. 2. Using geometric shapes to illustrate abstract concepts. For example, geometric vectors can help in understanding linear space and operation of them. Using animation to demonstrate process and transformation. For example, animations can help in understanding the process of differentiation or integration. 3D visualization to demonstrate concept of differential geometry, such as surface curvature and Gaussian lines. Using 3D visualization allows for creating complex models of mathematical objects that can be difficult to imagine in ordinary space. An example where visualization helps solve the Cauchy problem, allowing students to perform elements of qualitative analysis of integral curves. Students analyze the corresponding process by constructing a fragment of the corresponding integral curves and attempt to predict what other integral curves will look like. It is important to analyze the content of general and particular solution. The content of the general solution allows one to understand the dynamic of the process and its behavior in the victim of central points. Analyzing such situation allows students to understand the significance of mathematical modeling. For instance, the graph of a particular solution indicates the presence of Menier's extrema, while the graph of the general solution characterizes the process differently near central points. The visual approach to learning mathematics fosters the ability to interpret information, present mathematically, accurately use mathematics to convey information, and solve problems. Students find the visualization of machine epsilon interesting. When construction graphs, machine epsilon can be used to visualize small difference between numbers that, although very close, still differ due to the limited precision of float point numbers. It is important for students to understand the significance of this area where prescience is crucial, such as numerical calculators or signal processing. The impact of machine epsilon on graphical representation can occur, for example, when interaction with graph or data where numerical value precision is important. Here are some situations where this can become noticeable. First, graph on functions. If a function's graph has value very close to 1, machine epsilon can cause expressions to be round to 1 when displayed on the graph, potentially losing some details in the visual representation. 2. Comparing values. When comparing numbers on a graph, machine epsilon can cause values that have small difference from 1 to be perceived as equal, affecting the correctness of graph analysis. 3. Processing graphical data. When working with graphical data, such as imaging, machine epsilon can affect calculation or value compression of pixels, impacting image of graph protection. Appropriate visualization helps students not only hear this information, but also understand that when developing highly precise algorithm or in tasks where high numerical accuracy is critical, attention should be paid to the impact of the machine epsilon. The assessment of the level of visual thinking information can be carried out using various criteria that evaluate students' ability to analyze, interpret, and use visual representation in the context of higher mathematics and engineering tasks. We propose the following criteria. First, graphical skills. Ability to create quality graphs of mathematical function and analyze their shape and properties. Ability to use graphs to solve mathematical problems. 2. Spatial thinking. Ability to determine and understand spatial relationships, especially in the context of vectors, matrices, and geometric objects. Using visual representation to solve problems involving three-dimensional space. Third, working with computer programs. Ability to effectively use computer-aided design (CAD) programs, and other engineering tools, using the visual capabilities of program to solve engineering problems. 4. Using visual representation in analysis and problem solving. Ability to use visual model to solve complex engineering problems. And study and analyze visual data to solve mathematical problems. 5. Visual communication. Ability to clearly and effectively present engineering ideas through visual means. Ability to prepare visual presentation and documentation. These qualities were used to develop tasks and assessment tools to evaluate the level of visual thinking formation in students of technical specialists. According to the research goals and hypotheses, the pedagogical experiment was conducted in the first semester with first-year students majoring in software engineering during higher mathematics classes. The aim of the pedagogical experiment was to determine the effectiveness of modern methods of presenting higher mathematics material based on visualization principles. Using mathematical methods of analyzing the result of the pedagogical experiment, an increase in the level of visual thinking formation and the level of mathematical preparation of the experimental group students compared to the control group students was confirmed.